Hello everyone, and welcome back to another episode on macOS internals. In this and the next couple episodes, we will analyze and understand how stack smashing protection works. We will work with CLang compiler to generate macOS 64-bit Mac-O binaries. For this, we can start with some very simple code which declares a buffer and then writes to the buffer more data than it can hold. It will copy into it whatever gets passed in the first command line argument. You can clearly see what the problem is here. If we pass more than 16 characters, this buffer will be overflown. As a consequence, this will overwrite the return address from the main function stored on the stack and the application will crash. Let's compile the code, at first without any special arguments. We will understand what's happening step by step. Here's the command line to compile it. When we run the program, we pass the string parameter in the command line. Let's see a quick trick to generate the long buffer parameter with Python. We can run python -c and then we can execute any Python code. For example, a print instruction for as many characters as we need. We could also use this directly into the command line when we launch our overflow program. Let's copy the string and run overflow with this as a parameter. We immediately get an illegal hardware instruction exception. The program crashed. This makes perfect sense. Let's disable stack smashing protection. Then see what's different. The new command contains the no stack protector flag. We will get another binary version, which of course it should still crash because we only disabled a protection. Now it's a good time to use a debugger and see what's happening under the hood. Because we disabled stack protection on the second version, we expect different behaviors despite the crash. Let's check. I like the LLDB debugger and I encourage you to try it. First, set up a breakpoint in the main function. Run it, and when it breaks, just advance a few instructions using ni. Notice here the call to string copy function. Looking at its name, it's a slightly different string copy. Notice the chk suffix, which refers to a safer version of string copy. What is the difference? This version will check the parameters that are passed to it and take into account the length of the buffer. The function has an additional parameter, which is the length of the buffer. That's the maximum amount of data that will be copied to avoid an overflow. Nice! That's a very good default safety net, which automatically created a wrapper over the old insecure string copy function. Remember, we actually had a call to string copy in our code, which got translated into string copy chk. In this case, we have a bad access error, but that's because we didn't pass any argument when we started the program in LLDB. So even with no stack smashing protection, there will still be another safety net in the automatically replaced string copy chk function. Since this video is about stack smashing, let's understand what the stack protection flag does. What kind of safety checks are introduced? I'm recompiling with default options, which include stack protection, and then use LLDB to peer under the hood. set a breakpoint in the main function, and let the program run until it's hit. Notice that there's another interesting function being called stack check guard. This might have something to do with stack smashing protection. It is called once here in the beginning and another time at the end of the code. We reached the crashing point. See here the bad access error. Let's disable the main function to understand the logic of this check. The disable -frame command is very useful. We want to view the main function. The program already terminated because of the crash. Let's run it again. So if we disable this, we'll find that there is an access in the beginning to a memory address labeled stack chk guard. A value is read and then moved into a register. Then, at the end of the program, we will find the check. The location labeled stack check guard is being accessed. This basically verifies that the stack of the function did not get overwritten. This is the check introduced by the stack protection flag. The other check relates to the string copy operation, and it's something different. It comes from another flag. The flag is called Fortify source and is responsible for replacing vulnerable functions with safer versions. In this case, string copy was replaced with string copy chk. Let's now recompile with that flag disabled and see the difference. I'll disable both the stack smashing and Fortify protections. Then we'll debug and check the generated assembly code. Notice that now we have no stack guard check label in the beginning or end of the main function. And also, we have the basic string copy function, which doesn't verify the size of the buffer to prevent overflow. In case this is a bit confusing, I want to clarify again that we're talking about two different situations here. The first one is a protection against overflow for the stack of a function, which makes sure that at the exit from the function, its stack is in a safe state, and the return address has not been compromised. The other check is actually a protection for vulnerable functions. In our case, it makes sure that the number of bytes being copied is not greater than the size of the buffer. Let's play with this a bit and create another buffer here. For example, a bigger buffer which can hold 1000 bytes. Now, even if we overflow the first small buffer, this shouldn't destroy the stack as it happened before. I will compile without Fortify source protection, but leave the stack protection on. It should not trigger any crash. Let's check. So, disable Fortify source. If we were to leave that on, we know that the copy operation would be prevented. We care about the stack in this example. Even with stack protection on, if we overflow the short buffer, we shouldn't crash. The overflow will overwrite elements of the bigger array, but will not destroy the stack. Of course, only if the overflow is not big enough to overwrite both of the buffers. Having the ability to overwrite data without triggering a crash is very important while writing an exploit because it will keep it running. let's pass a long 100 bytes parameter to be copied and see what happens. No crash, although we've clearly written past the boundaries of the first buffer and into the second one. Because the stack was not corrupted, the execution will continue as planned after exiting the current function, which is main. To recap, we still managed to overflow one of the buffers if Fortify source protection was off. In the next part, we'll move up from the assembly view and use Ghidra disassembler to gain more information. Thank you very much for watching. Stay tuned and hope to see you in the next part. Cheers!